go ahead and get started. So again, my name is David Panthagani with NuGen Automation. On behalf of our panelists and presenters shown here on screen, and NuGen and our partner KROHNE, I'd like to very much thank all of you for taking the time out of your schedules to attend and participate in this webinar. It's part of our Insight series, which we started earlier in the year. This one specifically focuses on what we call it as our leak detection masterclass, focusing on principles and kind of the history, past, future, and present for leak detection. We'll quickly go through some bios and some logistics here in a few moments, but I wanted to also let you know that we will provide a handout to this webinar at the end of the webinar, and also, of course, that handout will contain links to the bios on LinkedIn and other material that we will share. This is the first of several webinars that we had planned this year. Primarily wanted to use this as a vehicle just to inform our customers and the industry at large on changes that we might be seeing in the regulatory landscape or new technologies that we're aware of. This one specifically, knowing that the compliance landscape here in the near future is going to change. With the support of our partner KROHNE, we wanted to focus and educate our customers and industry partners on just leak detection basics. So very much want to thank KROHNE for their partnership in pulling this together with us. Next slide, Mike. So just to provide a high-level background to NuGen, in case you guys are not familiar, many of our customers are on the call. NuGen started in 2010, primarily focusing on SCADA and IT service offering for our customers at the time that maintained their own control room. We grew to include a compliance group, a leak detection group, of which KROHNE was a partner early on, and a data analytics team, all focused on, again, providing these services to our control room customers. In 2018, NuGen was acquired by Linestar, and with that acquisition came a third-party control room business, was formerly EMS, along with a GIS team. And then lastly, in 2019, Linestar also acquired ROC, which was a third-party control room provider out in Katy, and its sister company, the Compliance Group. So Linestar is organized, as you see here, as this Advise, Connect, and Respond. Advise being the Compliance Group, which provides compliance advisory services through asset evaluation, documentation, consultancy, and they also do audit support. NuGen falls squarely in the middle here as Connect. We can build out SCADA IT infrastructure all the way to your field and now bring it back and control and operate it within our own control room. And then lastly, Respond. Tucker Construction provides pipeline and station maintenance, integrity digs, and small cap construction. The next slide, Mike. So many of you already know we've done our best to communicate our plans for 2020 with our customers, but wanted to provide a quick update. We, of course, undertook some significant integration activities with Linestar, including acquisition and integration of the ROC business. Part of that also is a capital construction here at our Ellington facility to consolidate those two businesses into under one roof and into one infrastructure. We push out a new website, so I'd encourage you guys, if you haven't yet, poke around on the site. I think it does a good job of explaining who we are, what we do, and also how we go about doing it. We also started the Thought Leadership series back in February. This is, again, the first of the webinars that is one facet of that. We're also doing a lot of web content, white papers, and blog posts, of which Jere and Whitney have contributed significantly. Of course, in March, we implemented our contingency planning, made many of you aware of that. And we took that opportunity to put all of our planning and materials on our website. So we have a COVID-19 hub there, bringing together resources from PHMSA, API, government regulatory bodies, just to provide one place where we can kind of collaborate and learn on something that many of us did not have a playbook for. We took that opportunity also to focus on our field automation and controls group, made that visible on the website, and then our Go Kit for control rooms made that visible as well. Knowing many of our control room customers are having a plan for these contingencies, wanted to present options to help them continue their operations. And then finally, we're finishing up here in May and June with knocking out some key milestones as part of the LineStar integration as it relates to rock. Next slide, Mike. Okay, yeah. So just some logistics, P's and Q's. If you guys have any questions, please use the control panel chat to ask. We will answer them at the end. So John is going to provide the bulk of the presentation, and then the panel is going to be open toward the end of the call, where we'll field the questions that people have already asked online up through last night, and then any new questions that get asked here during the webinar. And I would ask, if we're all working remotely, so if you hear kids or stuff in the background, just please bear with us. Yeah. All right, and special thanks yet to John for pulling together the bulk of the material. He's going to do most of the talking here. Daniel, of course, is calling in from Duisburg, so very much thank Daniel. Whitney and Jere have really provided much of the compliance leadership as it relates to this material and what we put up on the website. And then lastly, Mike, who's helped make this presentation as seamless as it has been. So it looks as good because of Mike's input. If there are any gross mistakes in it, I'll take ownership for those. Yeah, so the next two slides are kind of a high-level bio to John. So John's really the product expert for flow meters for KROHNE and has got depth of years worth of knowledge in this space, who's pulled together the presentation. And then Daniel's been a key partner and kind of key champion for NuGen. And we've worked with Daniel for the last several years, 3-4 years, really building the partnership. Also want to make mention that Angelo Delbuano there with KROHNE. And with that, I'm going to pass this over to John. And John, you can take the reins.
Okay, thank you, David. And let's just verify I'm getting the correct view for you. And we've got it. Okay, welcome and thank you for attending our session today. And our collaboration with NuGen is strong for providing these solutions. This session will provide you with a fundamental understanding of the operating principles of currently available leak detection technologies. Let's have a look at the topics to be covered. So upon completion of the session, you'll have gained insight into the historical development of pipelines and you'll know why they are monitored for leaks. The requirements and regulations placed upon leak detection systems will be explained briefly, and they can be more in-depth explained if you have questions. You will be familiar with various causes of leaks and will be aware of the different leak detection options available to you. You'll also be shown how pipelines are monitored using either non-continuous or continuous external or continuous internal, which is the most common leak detection systems. Today's pipelines originated in the second half of the 19th century. While drilling for water, crude oil was accidentally discovered in underground reservoirs. This crude oil was not very popular until simple refineries came into existence. The oil was transported to these refineries in wooden vats that were originally transported across rivers via barges, even pulled by horses. One alternative method of transport was by way of railway tanker cars. However, this meant that the oil was controlled by the railway owners. These were very large monopolies at the time. So to make transport independent and more reasonably priced, pipelines were adopted as a more economical means of transportation. The transported oil was then boiled off in refineries to obtain the byproducts of naphtha, petroleum, heavy crude oil, coal tar, and benzene. The petroleum was used as fuel for lighting and was very popular, and the benzene at that time produced was initially considered an unwanted byproduct and at that time was disposed of. This situation changed drastically with the invention of the automobile, which drastically increased the use of gasoline or benzene. Pipelines today transport a wide variety of materials, including oils, crude oils, refined products, natural gases, condensates, processed gases, as well as fresh, produced, and salt waters. Today, there's some 1.2 million miles of transport pipelines around the world, and some with well over 1,000 miles in length. The total length of all these pipelines lined up end to end would circle the Earth 50 times over. The construction of longer pipelines with larger diameters also increases the need for more intelligent leak detection systems to better detect and localize any unwanted releases. Whereas once enough to have inspectors walk the length of pipelines and visually look for leaks, today this is no longer possible. In many cases, due to the longer lengths and rigorous runs of remotely located pipelines, physical access may be limited. Pipelines can run through snowy landscapes, across mountain ranges, along bodies of water, or be located even underground at depths of up to or exceeding 1 mile. But why is it necessary to implement leak detection systems at all? Although pipelines are the most reliable and safe option compared to other methods of transportation, accidents and thefts can and do occur with pipelines. In such cases, leak detection systems can help minimize the damage to people, to the environment, and the company image, which is significant these days, as well as the high cost for repair, renovation, indemnity, breakdowns, and of course the lost value of the liquid or gas that has been released. And again, most cases that's least significant in the case of a accidental leak. In addition, there are also different official regulations related to pipeline leak detection. Let's have a look at those. In many countries, it has become necessary to observe official requirements in order to ensure safety of pipelines, particularly for hazardous materials. These requirements include the German TRFL, loosely translated Technical Rules for Pipelines. In the US, it's API 1130, which deals with computational pipeline monitoring for liquids. API 1149, which deals with the variable uncertainty of pipelines and their effects on a leak detection system. The former API 1155, which contains performance criteria for leak detection systems. This has since been rolled into and included in API 1130. And the American 49 Code of Federal Regulations, 49 CFR 195, which regulates the transport of hazardous liquids via pipeline. Up in Canada, it's the Canadian CSA Z662 that regulates oil and gas pipelines. But regardless of the specific national regulations, these rules are observed internationally and often form the basis for the selection of a suitable leak detection system. As we've just shown, leak detection systems are subject to official regulations. Leak detection systems must be sensitive, reliable, accurate, and robust. Sensitivity is a combined measurement which takes into account the minimum detectable leak rate, as well as the time it takes until a leak is detected. Here it is best to indicate the total leaked volume that escapes until the leak is detected. Reliability means that false alarms are avoided, but the actual leak events are reliably detected. Accuracy refers primarily to the localization of leaks. For example, leak location information is indicated in units of length, and accuracy information in percent of the entire length or pipe segment or instrumentated segment. Robustness refers to the operation of the pipeline leak detection system under less than ideal operating conditions. This includes things like sensor failure. In this event, pardon me, I'm having to scroll to two screens. This includes things like sensor failures, particularly flow, pressure, or temperature. In this case, the leak detection should be able to detect the failure and at least continue to work, albeit with reduced sensitivity. When evaluating individual leak detection systems, you should weigh each of these individual criteria against one another and not decide based on a single specification. And it's important to note that you can't just take and give a specification. It's very, in most cases, very determinant on the actual pipeline conditions, the operations, the layout, so very specific to the site. Before we take a look at how leak detection in pipeline can be done, let's take a look at what causes leaks. Fatigue cracks are one cause. These occur as a result of material fatigue and often found along longitudinal welds. Tensile strength can cause stress tears, which can reduce the effectiveness of cathodic corrosion protection systems, resulting in corrosion on the pipeline. Of course, stress corrosion is another issue. Cracks can also be caused by hydrogen indexing. In this, atomic hydrogen diffuses into the metal grid, forming molecular hydrogen. This can lead to the pipe material embrittlement and prone to early failure. Material manufacturing errors can also cause leaks. Example, when cavities have been rolled into the material during production of the pipe. And leaks can also occur when an external force acts on from the outside. This is the case when, example, a backhoe digs up a pipeline or a seismic event causes ground movements, causing shifts in the ground and breaking the pipeline. Leak detection systems would be categorized into two major types. There's either continuous or non-continuous methodologies or systems. The non-continuous system includes inspection by helicopter or fixed wing airplane, smart pigging, and tracking dogs, believe it or not. Continuous systems can in turn be divided into either external or internally based systems. External based systems include things like fiber optic, acoustic systems, semi-permeable sensor hoses, and even video monitoring. Internal systems, which is what basically API defines as computational pipeline monitors, or CPM. Internal systems include things like pressure point analysis, mass balance methods, statistical analysis, real-time transient model-based systems, and the latest evolution, the extended real-time transient model systems. In practice, non-continuous systems are often used in conjunction with continuous systems. In fact, I know in the US you're regulated to walk or fly your pipeline no longer than 2 weeks between inspections. As we saw in the overview of leak detection methods, inspection by helicopter is one option for detecting leaks. The helicopter flies along the pipeline looking to detect any outflowing gas. Three common methods when detecting leaks by helicopter include detection using laser, infrared cameras, and leak sniffers. When using lasers for leak detection, a laser is set to the absorption wavelength of the medium to be detected. When the laser hits the medium, a part of the laser energy is absorbed. The amount of energy absorbed from the laser is measured to arrive at the amount of leaked medium. Detecting leaks using infrared cameras functions by using video cameras that are fitted with a special filter that highlights a selected spectrum of infrared wavelengths. Certain hydrocarbons absorb infrared radiation from this spectrum, and leaks are detected as a visual indication, similar to smoke in the video image. Leak sniffers draw in air. I'm sorry, I passed by that. Leak detection using okay, I've covered that, I'm sorry. My apologies. Leak sniffers actually draw in air samples to evaluate in an analyzing unit, directly measuring the concentration of any leaked medium. To do this, the helicopter, of course, must fly slow enough to pass through the gas cloud made by a leak. The analyzing unit then indicates whether gas is present and in what concentration. Helicopters are a good option for detecting small gas leaks when the pipeline route is suitable for accurate flight routes. However, the accuracy also depends on the weather conditions. Poor weather conditions mean that the leaking gas can drift. In severe cases, the helicopters cannot even fly. So during extreme weather, monitoring using this methodology would not be possible. And that's the image I skipped over, my apologies. And the sniffer unit. Pipeline pigs are utilized for a variety of tasks in the pipeline integrity management field. This includes inspection, of course, of pipes and gauging, cleaning the pipelines. They use separating pigs for product batches, as well as gauging, as I mentioned. It can help gain valuable information about corrosion, cracks, wall thickness, as well as existing leaks in the pipeline. In this case, we use the term smart pigging. To perform pigging, a pig is inserted into the pipeline using a pig launcher. The pig advances through the pipeline, propelled by the medium, and gathers data along the way. A receiver is used to guide the pig out of the pipeline in order to subsequently collect and analyze the data. Various techniques are used to collect pipeline information using smart pigs. Two of these are the magnetic flux leakage method and the ultrasonic principle. With the magnetic flux leakage method, a strong permanent magnet is used to magnetize the pipeline. Any changes to the wall of the pipe, such as corrosion, change the magnetic flux lines, which are then recorded by sensing probes attached to the pig. Following pigging, the recorded signals are evaluated based on reference signals to detect any defects or abnormalities in the pipe wall. When it comes to the method based on ultrasonic principle, the pig transmits ultrasonic pulses into the line and receives their reflected signals. The signals are reflected by the inner and outer wall, and based on the running speed of the pig, the thickness of the pipe wall can be derived. By using smart pigs, existing leaks can be detected as well as damage to the pipeline, which could result in leaks. Pigs fitted with acoustic sensors can listen for a leak, for instance. Prior to commissioning pipelines, they are often pigged, and the results are used as a baseline for further inspections. This is called zero or baseline pigging. It is important to ensure that the pipeline is piggable in the first place. This means that you must be certain that there are no obstacles in the pipeline, such as restrictions or fittings, making the passage too narrow, and that there are pig launchers and pig receivers to capture the pig. In addition, the speed of the pig must be kept between 3 to 15 feet per second to obtain accurate results. That's quite easy in liquids. That's normal flow velocities. However, that can be a challenge in gas pipelines. That is a fraction of what their typical velocity would be. Another non-continuous solution for monitoring for leaks is the usage of tracking dogs. These dogs are specially trained to recognize the odor of a certain compound. This compound is injected into the pipeline to be inspected. The pipeline is then operated as usual, and the dog is led along the path sniffing for this compound. Very precise sensor our dog knows. The use of tracking dogs usually takes place with short pipelines or segments of pipeline. It's also a good method when it is not possible to accurately locate a leak using other methods, and then the dogs can be used to further narrow down the leak site. However, it is difficult to certify a tracking dog as a certified or regulated leak detection system, particularly within the framework of something like API or TRFL. The use of fiber optic cables for the continuous external monitoring leaks is based on physical changes that occur at the leak site. One of those physical changes is a typical change in the temperature profile, particularly with gases, not so much in liquids, but with gases for sure, due to the Joule-Thomson effect. To detect such leakage, the fiber optic cable is placed along the pipeline. A laser then emits pulses that are reflected by molecules in the glass. The reflected laser pulse magnitude gives insight as to the temperature at the place where the photon hits the molecule. By adding these reflections, a temperature profile can be made, and it is then possible to detect the characteristic change in temperature that would occur at the site of a gas leak due to that rapid cooling or Joule-Thomson effect. Monitoring pipelines with fiber optic cables is a good option for accurately localizing leaks. However, use of this method is only possible up to limited lengths of pipeline, and many reflections are required to plot a useful temperature profile, so it's very data intensive. When installing the cable, it is also necessary to pay attention to the medium to be monitored. If it is a gas to be monitored, the cable, of course, should be installed above the pipeline as gas normally rises. When it comes to liquids, it makes sense to install the cable below the pipeline as liquids would tend to sink. Detecting leaks using acoustic signals is possible through an acoustic signal. It's created because an acoustic signal is created when gases or liquids flow through a crack or hole in the pipeline. Acoustic sensors are installed outside of the pipeline to detect leaks by measuring the acoustic noise levels, and typically at multiple sites along the pipeline. This information is used to create a noise profile of the pipeline. Deviations from the baseline noise profile that are created result in a leak alarm going off. Acoustic sensors can be mounted directly on the pipeline, or they can be coupled to the pipe wall using steel rods for underground pipelines. To monitor longer pipelines, a large number of acoustic sensors are needed. Small leaks whose acoustic signals are small and only differ slightly from the background noise cannot be detected, as otherwise there would be many false alarms. And of course, noisy areas where heavy traffic, for instance, truck traffic, could create high background noise. Detecting gases using infrared is possible through video cameras featuring special filters, which are sensitive, to a selected spectrum of infrared wavelengths. Certain hydrocarbons absorb infrared radiation from this spectrum. This makes it possible to detect the leaks as an image of smoke on the video display in the case of gases. Liquids can also be detected using infrared cameras, as the thermal conductivity in wet ground is different than dry ground. In this case, you get a different temperature pattern above the leak position. Video monitoring of pipelines is designed for short distances or on company property. It is thus an interesting option in critical areas such as on company premises or high consequence areas. For its use as a continuous leak detection method, however, it's important to note whether the leak detection system, leak detection would occur automatically, or it would have to be manned and somebody actually visually see it and alert. So whether the system has the capability to declare a leak or not. When using sensor hoses, this is really typically done on chemical plants in very toxic environments. But here a sensor hose, a semi-permeable hose, is installed along the pipeline. In the event of a leak, the medium comes out of the pipeline and into the hose. In a time cycle, a test gas is injected into the hose and pumped through it. Then the contents of the hose are pumped to the end of the pipeline. There is an analyzing unit at the end, which then tests the hose contents for the presence of the particular hydrocarbon or toxic gas or liquid. The runtime of the test gas indicates the total runtime or length of the pipeline. As the total runtime is known, the difference between the arrival time of the medium signal and the length of the pipeline can be used to derive the leak site. Due to the material-specific properties of the hose, the use of sensor hoses usually only takes place in very short pipelines. The analyzing units can detect very small volumes of substances, meaning even the very smallest of leaks can be detected. Just as with fiber optic cables, when installing the sensor hose, pay attention to the positioning of the hose, either above or below the pipeline. Before we look at the individual methods of internal continuous leak detection, let's first look at the basic functioning of these systems. When there's a leak, the pressure and flow patterns in a pipeline change. These changes are recorded by the instrumentation, and the SCADA system transmits them to the control room. The system then calculates whether there is a leak in the pipeline, and the operator is informed at the HMI of the current status.
Wie wir bereits kennengelernt haben, gehören zu den kontinuierlich arbeitenden internen Systemen die
Sorry about that. Continuous internal systems are based on the following principles: pressure point analysis, mass balance, statistical, and real-time transient model, and the newest extended real-time transient-based model systems. Pressure point analysis is based on the evaluation of pressure drop or the pressure profile measured at individual points. As a spontaneous leak brings up a characteristic negative pressure wave, you can check whether the measured pressure drop dP within a time period dt exceeds set thresholds. In addition, a lower threshold for the absolute pressure is determined, and if either one of these events occurs, the system triggers an alarm. Another type of internal leak detection system is based on Antoine Lavoisier's conservation of mass principle. According to this principle, mass is a mass in a closed system, which we hope our pipelines are, remains constant and is not changed by processes within the system. If the pipeline is considered to be a closed system and you compare the mass flow at the inlet and the mass flow at the outlet, the difference in those mass flows in a leak-free case should always be zero. If, however, a leak occurs, the system has been opened and mass escapes. This results in a decrease in the measured mass flow at the outlet and an increase in the mass flow at the inlet. The problem with this type of leak detection is that it does not take into account dynamic changes in the content of the pipe, often referred to as line pack. This can happen, for example, when more product is being produced for a gas pipeline than is currently being consumed, and the pipeline pack serving as a large tank or cache. This type of leak detection is thus also known as uncompensated mass balance. Statistical leak detection systems subject a previously determined variable to a statistical test. A common statistical variables include pressure change over time or the result of a mass balance. The so-called hypothesis test is widely used here. With this test, two hypotheses are prepared, namely hypothesis 0, a no leak condition, and hypothesis 1, a leaking condition. The system checks whether there is enough data for a statistical variable to be a plausible part of the leak hypothesis, and if it is, sends out an alarm. Real-time transient models, or RTTM systems, can compensate for dynamic changes. To do this, they make use of basic physical laws which the pipeline must obey. The conservation of mass principle, which includes the density rho, the time t, the flow velocity v, and the pipeline location coordinates s. The conservation of momentum principle, which includes the flow velocity, the time, the pressure p, the pipeline location coordinates, and the pipeline friction factor, Fs. And lastly, the conservation of energy principle, which includes the enthalpy, H, the time, the density, the pressure, and the specific loss performance. These physical principles precisely describe the stationary as well as transient behavior of the flow in the pipeline. Using these equations of flow, pressure, temperature, and density can be calculated and integrated in real time for each point along the pipeline. These trends are also known as hydraulic profiles and accurately predict the true performance along the entire pipeline. But how do we actually detect leaks? To answer that question, let's take a closer look at the individual measurements. At the inlet, the pressure P0 and the temperature T0 are measured, and at the outlet, the pressure PL and the temperature TL are measured. Using these measurements along with detailed knowledge of the pipeline geometry and the properties of the product being transported, the leak detection system calculates the actual change in pipe contents or line pack. This is subtracted from the difference between the measured flow values F0 at the inlet and FL at the outlet, and results with the current compensated leak rate of the system. We also talk about real-time transient model compensated mass balancing. Extended real-time transient modeling systems use the same principle as the real-time transient modeling systems. The pressure PO and temperature TO are measured at the inlet, and the pressure PL and temperature TL are measured at the outlet. Using these measurements, the leak detection system calculates, using the laws of physics, expected flow rates at the inlet and outlet. These expected values are then compared to the measured flow values, F0 at the inlet and FL at the outlet. Here we obtain the so-called residual values, where X equals the measured flow at the inlet minus the calculated flow at the inlet, and Y equals the measured flow at the outlet minus the calculated flow at the outlet. In a leak-free condition, both X and Y should equal 0. In the event of a leak, we see deviations where residual X is greater than 0 and residual Y is less than 0. And that's due to the increased flow when a leak occurs due to less resistance in the pipeline on the inlet, and reduced flow on the outlet due to product escaping on the outlet. In order to avoid false alarms, extended real-time transient model systems also use leak pattern recognition. This system uses the residuals X and Y as decision values, and a leak situation is not the immediate result of a deviation. Let's take a look at residual X. Leak pattern detection accesses an expandable database of different leak signatures and can thus differentiate between accidental interference, such as instrument drift or spike, and a true leak. Thanks to the special type of signal evaluation, small leaks can reliably be detected and false alarms avoided. Now that we have know how the different internal leak detection systems function, let's take a look at their capabilities. pressure point analysis shows a typical minimum detectable leak rate starting at around 5% of normal flow through the pipe. Detection time for liquid pipelines is short, but for gas pipelines it is long, and only spontaneously occurring leaks can be detected. So slowly developing leaks cannot be detected. The frequency of false alarms is relatively high. With additional pressure gauges, high accuracy when it comes to localizing leaks is possible, depending on the sensor sampling rate. Mass balance methods can typically detect leaks starting at 1% of normal flow in the pipe. The time needed to detect leaks for both liquids and gas is longer, but creeping leaks or slowly developing leaks can also be detected. The frequency of false alarms is high in this case as well. The accuracy with additional pressure gauges is average when it comes to leak localization. Statistical methods generally detect leaks starting at about a 0.5% leak rate, but the detection times are longer. You need enough data to satisfy the statistical hypothesis. Both spontaneous and creeping leaks are detectable, and the frequency of false alarms is reduced with this statistical analysis. If additional pressure gauges are used, leak localization is fair in terms of performance. And then real-time transient model-based systems detects both spontaneous and creeping leaks quickly. So the big change now is fast response to the leak due to the modeling. With a typical minimum leak rate starting at 1% of typical normal flows, the frequency of false alarms is average, and the accuracy in terms of localizing leaks is high. The extended real-time transient systems can still detect leaks in liquid pipelines very quickly and in gas pipelines quickly, and start at a 0.5% leak rate, detecting both spontaneous and creeping leaks with high accuracy. And the frequency of false alarms now is drastically reduced by way of pattern recognition. Now that we've completed the leak detection session, you have a basic overview of the historical development of pipelines, and you know why pipelines are monitored for leaks. You know the requirements placed on leak detection systems. You're familiar with the various causes of leaks and different leak detection options. And you've also learned the basics of how non-continuous, continuous, external, and internal methods are functioning. So that completes our session for today. There is another part on, we can go in, no, I think that's it. That's looping back around. So I can stop there, pass it back to David.
Thanks, John. Very much appreciated. To everyone on the call, I know it was kind of a lot of detail to gather, but we did want to provide the various methods that are available, and then kind of finish out the full suite, going from internal, external, and ending up with the high fidelity model-based systems as well. So thanks, John, for that. And again, just a little bit more background before we get to the Q&A, so you guys have asked some questions, but any more that get asked. Daniel heads up the pipeline solution management group for KROHNE, specifically responsible for Pipe Patrol, which is their premier leak detection suite. And then John is the ultrasonic flow meter product specialist with KROHNE, with a significant background, over 2 decades of work in this field. So we had 4 questions asked previously, and then we've got a couple others asked here in the last hour or so. So Daniel, I'm going to throw the first one to you. Here's the question. Can you perform leak detection on a crude oil system without correcting flows to standard barrels?
Okay, great. Thanks, David, for the question. Yeah, in principle, the answer is quite simple. So it's yes, we can. The reason for this is there are 2 reasons, or two possibilities. So first thing I would like to add here is that our system is able, the pipe patrol system provided by NuGen and KROHNE, is able to correct the crude oil to standard conditions on its own based on the API calculations. So if pressure and temperature and information on the crude oil is available, the system can do the calculation without any external other system or flow computer. However, if this question was asked because there might be systems where this instrumentation is not available, this possibility, this is also possible. So the system can also work with process conditions. So with process flow conditions and accept the deviation, which may occur in this case as the statistical normal, because it uses pattern recognition. So these are the two possibilities, and in both cases, the answer is yes, we can do this.
Thanks, Daniel. The second one, I think, is between you and John. The question is statistical versus model-based leak detection software and pros and cons of each. So I think it's covered in that one slide that John mentioned, but maybe just a quick touch on pros and cons between statistical and model-based leak detection.
Okay, John, if you don't mind, I will take this question and answer on this.
Yes, that's for you, Daniel.
Okay, so yeah, so if we look at statistical systems, I would say the main performance indicator or performance characteristics of those systems is that they are very reliable, yeah, because they try to achieve a very high confidence into the decision if there is a leak or if there's no leak. But this makes our system typically slow, which means depending on the pipeline, depending on the product in the pipeline, they have this uncertainty in line pack calculations, and they take a lot of statistical samples, a lot of time to come to a conclusion if there is a leak or if there is no leak in the pipeline. So then we have the model-based systems, which are very accurate because they do the line pack compensation based on a model. So they have all the hydraulic information available. They can work very well on multi-product pipelines. And with this hydraulic information, they are able, for example, to detect slack lines without slack line conditions without additional information. But they also put high demands on the instrumentation, but they are accurate and fast. So with the pipe patrol system, we have a system which, at the end of the day, combines those two principles into one system. So we have the reliability of the statistical system in combination with the accuracy and the sensitivity of the model-based system. And because it uses the pattern recognition, it's also very fast. So it also improves the sensitivity in terms of detection times. So with this unique combination, real-time transient model with statistical pattern recognition, we have a system which provides the best of both worlds.
Thanks, Daniel. I'll take the next one. The question is, interested to hear if and how IoT technologies, so this is the Internet of Things, are being used for pipeline integrity solutions, data retrieval, timing requirements, and its effects on calculations. So I'll take the first half of this and maybe I'll kick it to you, Daniel, for the second half. So we're starting to see more and more IoT capable field devices and SCADA system compatibility. So these are MQTT brokers or edge devices that can provide a significant amount of data as a report by exception. So as opposed to the continuous 30-second polling intervals, these instruments are just reporting up when they see a change. So they can potentially be more accurate on when they report the timing of what they see. As it relates to implementation, we've not seen any leak detection system yet paired with IoT or MQTT brokers that we've seen in NuGen's experience. I'm certain people are starting to observe benefits, but maybe Daniel, if you can speak to sensitivity and specificity matters when it comes to like timing of data.
Yeah, absolutely. So IoT is a big thing, and it's also a great chance to improve every leak detection system. So, I mean, of course, if we do this transmittal on change, dead bands should be low and time synchronization should be secured. But in this case, if this is okay, then it definitely approves for real-time transient model-based system. It will improve the modeling, so the line pack correction or compensation or the uncertainty in line pack will be lower. Also improves the shape of the leak signatures. So this, at the end of the day, improves the sensitivity and the localization algorithms, at least for I can speak for our system here. And yeah, with the Internet of Things, you already named it. We have the possibility to include more instruments into the system. So gather data at points where it has not been possible maybe before. So we get more information from the pipeline. More information means better systems, better sensitivity, better protection. And we can use all this kind of different communication. I mean, there is like wired communication, fiber optic, wireless communication through that satellite or whatever. So this is all possible. And last but not least, I would say, which is already reality, virtual solutions. Yeah, so running leak detection systems, virtual machines on cloud-based solutions. So this is more and more our daily business. And yeah, I think this will change and improve the industry a lot. So yeah, thank you.
Yeah, I'd like to add just a little bit there, if I could, David.
Yeah, go ahead, John.
Yeah, in addition, these tremendous potential, and I think the gas transmission pipelines particularly are seeing the benefits that new modern flow meters are microprocessor-based instruments with a lot of information. So rather than a simple turbine meter monitoring flow, for instance, where all you receive are pulses, you have no idea the health of that pulse. If the meter's been damaged, there's no additional information. If we were to swap that to a inline ultrasonic flow meter, we have tremendous amount of data on the gas quality, the signal strengths, all the key parameters of operation can be monitored continuously. So now a leak detection system doesn't have to guess if a meter is spiking because of a fault. It would know the health of the meter is good and that was a true operational condition, or it was an upset, and that the meter can actually advise and assist in that decision-making process. So data collection from meters is becoming very big.
Yeah, and then teeing on to both of those. So as it relates to bringing back the communication from these pressure points that we're adding out to remote pipelines, power requirements have significantly dropped for cellular modems, for example. So they're able to power them on solar, pair them with one of these virtual machines running some MQTT broker out in the field. Kepler and other vendors are making their products compatible with these infrastructure, so that then you can bring back data from sites that usually you usually never think to bring back to empower a leak detection system. Okay, I got a question here for Jere and Whitney. I'll let you guys pick here. So the question is there a preference when it comes to compliance on internal versus external leak detection?
Thanks, David. I'll take that one. Simply put, no, regulations do not require or show a preference for a certain type of leak detection. As long as the method can be shown to be consistently effective, any reasonable method can be employed for leak detection. However, do keep in mind that 195.444 does now require that operators evaluate their pipelines on multiple factors to determine the most appropriate method of leak detection. So operators must consider factors such as the length and size of the pipeline, the type of product that's being moved, how quickly the method of leak detection can respond, how long it would take for the nearest response personnel to arrive to get the response that's necessary, as well as the history of the pipeline in question when it comes to leaks. But as long as operators can show that they have taken these factors into consideration, most methods of leak detection will assist operators in maintaining the compliance and be considered by PHMSA. However, as a note, outside of the compliance aspect, we do encourage operators to consider other aspects such as cost. So depending on the length of the pipeline in question, for example, some methods such as monitoring by helicopter will carry a much greater overhead simply by nature of the pipeline itself. So it is beneficial for operators to consider all methods that meet the regulations and determine which method is best for the operator and the individual pipeline.
Yeah, good point, Whitney, bringing in overall considerations. One more question here.
David, may I add something here?
Yeah.
Maybe I really like what Whitney said, and just wanted to add that the pipe patrol system also allows it's really modular based, so it allows installation from very simple balancing methods, as a very simple line balance, and you can add module and module and module to the system. So depending on your assessment, on what kind of leak detection system you require for your pipeline, and we as NuGen and KROHNE, we can definitely support you as a customer to review your application and decide together what kind of system is the best in this case. And as I said, this doesn't necessarily need to be a full-blown ERTTM leak detection system, but this could also be like a smaller kind of system because it may be sufficient to achieve regulatory compliance. So, yeah. Thanks.
Thanks, Daniel. Yeah, good points. All right, one last question, again for Jere and Whitney here. So we will provide a handout shortly after the webinar that talks through some of the specifics of the 195.444 reg and overall mega rule implications. But here's this question here. How do the changes to the mega rule affect PHMSA CRM requirements?
Thanks, David. I'll take that one as well. Short and sweet, the mega rule changes don't change anything with control room management requirements with regard to 195.446 and 192.631. However, it does mean that aspects of control room management, so we're talking about things like documentation, incident investigation, and procedures, they're going to need to take leak detection methods into account. That's previously been done. It's always been a requirement. But as these additional changes are made to operators' leak detection methods, how they're employed, how they're being monitored, what their procedure responses are, how they're doing those investigations as a result of these changes, they all need to be documented and included in the procedures to ensure that operators are being consistent in what they say they do and actually doing it as well. So in short, it doesn't actually change anything with the CRM regulations, but operators do need to keep those requirements in mind when they go to make changes regarding their leak detection methods.
Thanks, Whitney. And yeah, as I mentioned, so Whitney and Jere have put together a quick handout that will summarize some of these criteria as well, and we will provide that shortly after. So that's all the questions that we've got. So Mike, yeah, if you want to put the last slide up, thank you. We'll just closing remarks here, folks, and then we'll sign off. Again, we will provide copies of the presentation. The webinar is going to be recorded. We'll also load it to our website shortly. I would encourage you guys, if you haven't yet, check out the NuGen site. We've got a lot of the content that Whitney and Jere have helped create around kind of compliance, control room, and just general white papers that we've put out there loaded to the resource page on the website. I also want to mention that NuGen and KROHNE are working on additional insight series similar to this. There's a pipeline management solutions webinar series that KROHNE is putting up, and they've invited NuGen to join with them on a few of those. So we've got a couple more of these in the funnel. So keep on the lookout for that. We've got the list of attendees here. We'll broadcast invites in a very similar fashion. And then pay attention to the handouts at the end of the webinar that contain contact details of the presenters and additional information for the material that was presented. There is also an exit poll at the end of this thing. So as you guys have time, provide us feedback. We'll certainly take it into consideration. In most cases, we take pride in thinking that NuGen is an extension of many of our customers' organizations. So we're very much interested in the feedback that you have to help improve our delivery. So on behalf of the panelists and all of the people that presented and poured into the development of the content here, I want to thank you all for attending, and please be in touch. We'll do our best to reach out with any answers to any questions that you may have as a follow-up. But I wish you guys all good health and that you stay safe. Thanks, everyone.